Good morning. Welcome to session G3, Hydraulic Analysis for Risk and Structure Evaluation. Hope you're enjoying the ASFPM conference this year. Too bad it's virtual, but next year, hopefully not. My name is Alan Luloff. I'm with the ASFPM Flood Science Center. ASFPM established the Science Services Program in 2007, and that transitioned to the ASFPM Flood Science Center in 2017. Please go to booth NEO2 to learn more about the Flood Science Center. Well, today's first session is going to be on the Cache River 2D floodplain analysis. And that'll be presented by Chris Hanstad. He's an engineer with the Illinois State Water Survey's Coordinated Hazard Assessment and Mapping Program, or CHAMP. He has over 10 years experience in floodplain mapping and H&H analysis. He's a licensed professional engineer in Illinois, Indiana, and Wisconsin, and a certified floodplain manager. And he's led the Illinois Lomar Review Partners program for 10 years. So with that, I'll let Chris get into his presentation, or he'll hear his recording actually. Oh, by the way,
all right, well, welcome everyone. Thank you for attending. My name is Chris Hanstad. I'm with the Illinois State Water Survey in Champaign, Illinois. And I'm excited to share some of the initial results of a very interesting floodplain mapping project for the Cache River Valley involving 2D modeling. Before I dive in, I just want to make a few acknowledgments. First, FEMA partnered with the Water Survey to develop floodplain mapping for the project areas that you're about to see, so special thanks to our funding partner. And secondly, the Water Survey has had a very long and extensive history of studies and modeling in the Cache River system. So I am by no means the resident expert when it comes to the Cache River. That title would probably belong to Laura Kiefer, who provided us with a lot of valuable data and information. And I also want to acknowledge my colleague Greg Byard, who provided input and direction for this effort as well. As I had mentioned, FEMA funded the Water Survey to develop floodplain mapping for a number of counties in southern Illinois. And to get a sense for where we are at the very southernmost section of Illinois, near the confluence of the Mississippi and Ohio rivers. So no big deal. It's not like those rivers ever flood or anything. Of course, I'm kidding. And the Mississippi and Ohio river flooding very much factor into the Cache River system. But to understand how they influence flooding, we first need to look at the history of this area. So here we're looking at the terrain of this multi-county area of southern Illinois, and we have the Mississippi River here to the west. We have the Ohio River to the south and to the east, and tucked right in between these two great rivers is the Cache River. And now you'll notice this very large flat swath of land that seems to be connecting the Ohio River and the Mississippi River here. We're generally referring to this as the Cache Valley. And the Cache Valley used to be the pre-glacial period Ohio River channel. And the modern day Ohio River channel used to just be the Tennessee and Cumberland River channel. And then during the last glacial retreat, the Ohio River intercepted much of the glacial outwash sediments. And as a result, the Ohio River bed began to erode until it forged a new path to join forces with the Tennessee and Cumberland River in its modern day course. So it left behind the old Ohio River Valley here, which we now refer to as the Cache Valley, but this valley still served as an overflow path for high Ohio River flows. But otherwise, drainage in this valley was primarily dominated by two watersheds. We had the Cache River, which flowed to the west, and Bay Creek, which flowed to the east. Then fast forward to the early 1900s, we had growing agricultural interest within the valley, and as a result, drainage districts were formed. And one of the early projects to occur in this valley was the construction of Post Creek Cutoff, which you can see right here. which effectively bisected the Cache River into two segments, the upper Cache River, which drained directly to Post Creek Cutoff, and then the lower Cache River, which continued to flow to the west. And then around the same time, we had a lot of construction of ditches throughout this valley, primary one being the construction of Main Ditch, which you can see here. Then in 1952, in response to the 1937 Ohio River flood, the Corps of Engineers constructed two levee systems within this valley. We had the Karnak levee here, which formed a complete separation of the upper Cache River from the lower Cache River, although that separation wouldn't last permanently. And then we had the Reesville levee, which served to prevent Ohio River from flowing into the Cache Valley, into Main Ditch and the lower Cache. And so what we're left with today is we have 3 Huckate watersheds within this vicinity. And you'll notice that these 2 levee systems are situated right on the drainage divide, the watershed boundary of these Huckate watersheds. So that's going to give you an indication that they're going to be critical to the overall drainage and hydrology of this valley. I'd mentioned the Karnak levee. This is what it looked like in 1985. You can see a couple culverts with flap gates, which allow drainage from the western portion to drain to the east into Post Creek Cutoff. And here's what the levee looks like after the 2002 breach. You can see segments of the culverts in the middle of this breach segment here. And this breach still exists today, although there are plans to repair this breach. Construction may start later this year on that repair. Given these unique historic alterations within the valley, there are several challenges to overcome for us to develop floodplain mapping for this region. First, the Cache Valley hydrology and hydraulics are very complicated, as we'll see here on a slide. Additionally, this is a very large spatial extent that we're working with here, and there are many discrete flooding reaches that have varying degrees of interdependence with the Cache River. And this is a perfect example of what I mean by complicated. We have the Cache River coming in here alongside the Karnak levee. Some of the flow moves through Post Creek Cutoff, some of the flow is moving through that levee breach into the lower Cache. And then you have all of these auxiliary flow paths, side channels that parallel the Cache River. So a lot of lateral flow areas where water can move in between these areas, and sometimes flow moves in the opposite direction of the main Cache River. Sometimes it moves in the same direction. It's very complicated, and anyone who has any experience with traditional one-dimensional modeling will recognize some of the complexities in trying to analyze an area like this. So finally, in addition to the complexity that we're dealing with here, we had to look at a lot of different flooding scenarios in this area regarding the levees, because neither the Karnak levee nor the Reesville levee currently have FEMA accreditation status. So we had to look at various scenarios regarding those levees and other man-made structures within this valley in order to satisfy FEMA mapping requirements. So we decided to use HEC-RAS 2D rain-on-grid to develop floodplain mapping for the Cache River Valley. And this simply means that we are integrating our hydrology and our hydraulics into the 2D grid by directly applying precipitation on this 2D grid. And so our 2D model needs to encompass all of the watersheds and contributing drainage areas to our area of interest. So what we're looking at here with this yellow polygon, this is our actual 2D model boundary, which spans most or parts of 8 separate counties here in Southern Illinois. So this is an enormously large model that we're working with here, and we're typically using 500 by 500 foot cell spacing, although we do have some regions with smaller cell spacing where it was needed, for a total of a little over 160,000 computational cells in this model. So now, even though we're using a cutting edge tool to analyze some very complicated flow patterns and various flooding scenarios, we still had new challenges to overcome. Namely that we haven't had any experience calibrating 2D models before, much less a 2D rain-on-grid model. So we weren't quite sure what to expect when we started calibrating this model. And even though we had a recent flood of record, a lot of data to calibrate to, we still had to figure out how to prioritize the calibration data and results to best fit the objectives of this project, which is to produce floodplain mapping. So we looked at the March 2008 flood for calibration, since it produced between 7 and 12 inches of rainfall in about 40 hours. And this flood event was the flood of record for the upper cache, which is shown in this vicinity right here. So we had a good event to calibrate to. And we also had a lot of data to use for calibration. We had 4 USGS gauges spread out across this modeling area, most important of which being the Cache River USGS gauge just north of the Karnak River. We also had high water marks that were collected throughout the lower Cache River and some along Main Ditch as well. And then we also had flood aerial imagery that was collected for this 2008 flood, which was interesting to work with and make visual comparisons for our modeling effort. Looking briefly here at the gauge calibration, we have here the Cache River gauge. We've got the, in red here, we're showing the gauge flow hydrograph here. The solid blue line is showing our uncalibrated 2D model results, and the dotted line is showing our calibrated 2D model results. So our initial runs were coming a little bit under in terms of overall runoff volume and peak flow. We were able to adjust some things and get the flow hydrograph to compare a little bit more favorably to the observed flow hydrograph. But really, we were more interested in stage comparison. So here's the comparison of the stage hydrograph. Again, red is showing the gauge stage hydrograph, and our dotted blue line is showing our calibrated stage hydrograph. And we're coming within a ½ foot of the peak gauge stage that was recorded, and we were able to achieve this at all of the gauge locations. So we're really quite happy that we were able to get really close on the peak stages recorded at these gauge locations. And then of course we had high water marks that we used as well for calibration. Now this area is near the Karnak levee, which you can see right here. So we've got the upper cache coming in, we've got Main Ditch coming in from the east, we've got lower cache to the west here, and we've got Post Creek cutoff to the south here. So this is really like the central hub of this entire model, and really a critical area for us to get good calibration and comparison results, because what happens in this area really affects all other areas of the model. And what we're showing is that our peak 2D model results for this calibration event are pretty much hitting right on the observed high watermark elevations. And then here on Main Ditch, our 2D models coming in about 0.3 of a foot higher than the collected high watermark. So we're really quite pleased with these results, especially in this area of the model. And then I mentioned we had aerial flood imagery that we could compare to our 2D model results. And so we're going to look at a few of these areas for comparison purposes. The first area that we're going to look at is the Cache River Belknap Road overflow, which is just northwest or northeast of the Karnak levee here. So what we're looking at is the flood aerial imagery. We've got Belknap Road here, we've got the Cache River up here, and the actual bridge for Belknap Road is a little bit further to the southwest. So this is all completely uncontrolled overflow over Belknap Road here. And so when we fade in our 2D model results, what we're seeing here at this location is our model is showing us the exact same thing. We've got uncontrolled overflow over Belknap Road here, and the overall inundation extents compare very similar to the flood aerial imagery. If we look to the south a little bit, the southern end of the Karnak levee where the breach is in Post Creek cutoff, we've got the Karnak levee here, we've got the levee breach here, so you can see water is moving through that levee breach during this 2008 event. We've got Post Creek cutoff here to the south. And when we fade in our 2D model results, what we're seeing again is a very favorable comparison with flow moving down Post Creek cutoff, and you can see some flow is also moving through this levee breach into the lower cache here. If we look just to the north here at the northern end of the Karnak levee near Belknap, we are looking at the upper cache coming down here. Here's the Karnak levee. This is a very complicated inundation area from this 2008 flood. And if we fade in our 2D model results, we're seeing our 2D models is very closely closely mimicking that aerial flood imagery that was collected. So one more area to show with this flood aerial imagery, a little bit further down the lower cache here near the town of Ullen. We've got the lower cache flowing to the west here. We've got Interstate 57. Here's the community of Ullen. And if we fade in our 2D model results, once again, we're seeing a very similar comparison of our flood inundation extents between the model and the flood aerial imagery. So this is very interesting comparisons that we can make with flood aerial imagery, and something that we hope to be able to take to the public and show them these comparisons. So while we're really excited and encouraged by the initial calibration results that we're seeing, the overall goal wasn't simply to produce a calibrated model. The goal for this project is to produce floodplain mapping for this region. And to do that, we had to undertake some scenario modeling, because as I had mentioned, we have some features within this area that really control or influence flooding within the valley. So we had identified 3 geometry features that have a pretty significant influence on flooding within the Cache Valley. As I mentioned, the Karnak levee. We modeled the Karnak levee as fully repaired. We modeled it also without, and we also modeled it in its existing breached condition. The Reesville levee we modeled simply with or without. Then we also had a bunch of high embankment structures like railroads, state routes, interstates that span the Cache Valley that can exhibit some backwater controls on flow that can attenuate flows within the valley. So we modeled these as a group simply with and without. And then we looked at 2 general flow conditions within the valley. We looked at the sunny day flood event, where we put no rain on grid for our 2D model. We only looked at 100-year flood conditions on the Mississippi and Ohio rivers. And then we looked at our 100-year rain on grid storms with 10-year backwater conditions on the Mississippi and Ohio rivers. So this matrix here is showing you all the combinations of model geometries that we utilize for our scenario modeling. We have our 3 Karnak levee scenarios here. We've got our with and without Reesville and our with and without high embankment structures here, for a total of 12 possible geometry combinations that we analyzed. And by the way, for calibration event, that 2008 event, we used the Karnak levee breach scenario coupled with the with Reesville and with high embankment structures, since the Reesville levee did not breach during that event and the high embankment structures were intact as well. So with each of these 12 geometry scenarios, we simulated the sunny day, the 10-day, 5-day, and 72-hour rain on grid events for a total of 48 modeling scenarios, and we'll probably add a few more before everything is said and done. So once we had run each of our 48 unique simulations, we were able to start comparing our results and understanding the impact of some of these features on flooding in the Cache Valley. And initially, our biggest question revolved around the impact of the Reesville levee, since it holds back the Ohio River backwater. And here what you're looking at is the Ohio River backwater against the Reesville levee, and we've got about 3 to 5 feet deep water against this, most of the reaches of this levee. So the big question in our mind was, if you simply remove the Reesville levee and you get this, does this flooding simply overwhelm and dominate flooding throughout the rest of the Cache Valley, since you have virtually limitless volume coming from the Ohio River here? And what we found was that no, actually the Ohio River overflow does not completely overwhelm the Cache Valley flooding. What we're looking at here is the maximum flood elevation profiles for a few different scenarios within the Cache Valley. There's a lot of information, so let me walk us through it. We're looking at the main ditch reach here. So we have the Karnak levee here to the west. We've got the Reesville levee up here on the east, and the solid lines show us the rain on grid flood events, the 100-year rain on grid flood events, and the dashed lines show us the sunny day Mississippi Ohio River backwater flood events. And the blue lines are showing us the without Reesville scenarios. The red lines are showing us the with Reesville scenarios. So it's not really a surprise that a blue line is showing us the highest flooding stages within this reach, since that's the without Reevesville scenario. But what was somewhat surprising was that it wasn't the Ohio River backwater that was sending the most flow and worst case flooding in the main ditch reach. It was actually the 10-day rain on grid storm that's giving us the highest flooding throughout this main ditch reach. It's only once you get between Interstate 24 and the Reevesville levee that you're seeing about the same flood stages for both the Ohio River sunny day flood and the 10-day rain on grid flood for the without Reevesville scenario. And to understand why this is, we had to look at the Reevesville levee influence on Bay Creek. And you'll remember that Bay Creek was one of the other main watersheds that come into this Cache Valley system. With the Reevesville levee, all those high flows on Bay Creek are forced to flow to the east towards the Ohio River. But as soon as we remove the Reevesville levee, those high flows on Bay Creek, once they reach the Cache Valley, are allowed to bifurcate, with a very substantial portion of that flow moving off to the west towards Main Ditch and the lower Cache. And this bifurcated portion of the Bay Creek flows are more or less the same as the Ohio River overflow for that 100-year flooding condition. Now, if we move down to the Karnak levee to see that the impact of the Karnak levee on flooding within the valley, what we're looking at here is the without Karnak levee scenario. So you see flows coming from the upper Cache, main ditch here. They're free to cross this the levee because it's not modeled in this scenario. So you see a lot of flow moving into the lower Cache from the main ditch reach here. If we look at the existing breach condition, now the flows from upper Cache and main ditch, they need to come and enter into the lower Cache only through this breached area here. So you get more flow moving through Post Creek Cutoff. And then finally, with the fully repaired condition here, all the flows from upper Cache and main ditch are forced to drain through Post Creek Cutoff, and nothing can cross into the lower Cache. So you're seeing the reduction in inundation extent on the lower Cache here because you have less flow moving into the lower Cache. So here's what the maximum flood profiles look like in this vicinity of the Karnak levee here. You can see the Karnak levee. We've got main ditch reach to the east, lower Cache to the west. And the red line here is showing us the with Karnak fully repaired scenario. So under this scenario, no flows from main ditch and upper Cache can make it into the lower Cache reach. So we're seeing the lowest flood on the lower Cache, but we're seeing the maximum flood stage for the main ditch reach, since all the flows need to drain exclusively through Post Creek Cutoff under this scenario. And the blue line here is showing us the without Karnak levee scenario. So this scenario is giving us the maximum flooding on the lower Cache reach because we're seeing the most flows move into the lower Cache from main ditch and the upper Cache River. But we're seeing the lowest flood stages on the main ditch reach, since flows from this area can move into the lower Cache reach. And the green line is showing us the existing breach scenario, which more or less shows us compromises of those two extreme conditions. And then looking at the lower Cache controlling 100-year flooding scenarios, we're looking at a reach between the Mississippi River confluence here all the way up to the Karnak levee. And you'll see that the Sunny Day or Mississippi River backwater controls flooding for much of the lower Cache River reach all the way up until about Interstate 57. It's only once you get upstream or to the east of Interstate 57 that suddenly the 10-day rain on grid events begin to control flooding for the lower Cache. And both of these two simulations are showing the without Reevesville and without Karnak levee, since we know that that controls flooding for the lower Cache. The red line is showing us the without structures, those high embankment interstates and state routes. That allows more flows to come through the lower Cache. So for some areas, this controls flooding. The blue line is showing us the with structures. And so some areas of the lower Cache reach, the with structures control because of localized backwater effects at certain structures. So here's what the structures with versus no structures looks like. With structures, we can see that the flow needs to constrict and move through these structure openings unless they're overtopped. And then if we remove those structures, we're allowing flow to pass across those embankments freely. So a few key takeaways at this point. Some things were not very surprising, and the results are consistent with what our intuition has told us. Number one, the Reedsville levee does affect flooding in the Cache Valley. That's not surprising. The Karnak levee affects flooding in the valley. That's not surprising either. Flooding on the eastern and western reaches of the Cache Valley is dominated by the Ohio and Mississippi backwater. That's not surprising. But what we were able to take away from this is an understanding of where those backwater controls, how far those extend into the Cache Valley. What we did find that was somewhat surprising at this point was that the 10-day rain on grid floods dominate flooding for the interior reaches of the Cache Valley. We were concerned that the Ohio River backwater would dominate flooding within the interior of the Cache Valley, but that's actually not the case. And also the 2D rain on grid model encompasses or compares very favorably to observed flooding conditions. We weren't sure what to expect with a model this large and using a relatively new method with this 2D rain on grid modeling, but we were pleasantly surprised with the favorable calibration conditions. So a few next steps for this effort. We've got some continued model refinement and review that we need to undergo before we're able to really roll out more detailed results. We'll have to continue coordinating between FEMA and the state about the various mapping scenarios and what should appear within this area. And we have a lot of GIS work to turn these model results into floodplain mapping. So we still have a lot of work ahead of us for this effort, but we are excited to continue with it. And that's all I have. So thank you very much for your time. If you have any questions, just let me know.
Well, Chris, that was a very interesting presentation and great graphics there today. I thought Illinois was flat, but according to that, it looks like you've got a fair amount of relief there. We've got a number of questions that have come in. And the first question that I'll read for you is from Will. It says, can you comment on Manning's N calibration versus expected values from the literature? Was the model sensitive to model resolution?
Okay, so with the Manning's N values, we started off with Manning's N values that were consistent with a 1D analysis. So we started off with kind of stock values for our Manning's N values across the 2D grid. Manning's is a little bit of an interesting calibration parameter when it comes to a 2D rain on grid model because it has some competing effects on the model. I think we're mostly used to in a 1D environment when you increase your Manning's N value, increase your energy losses, so your flood stages go up because of that. In a 2D rain on grid environment, it's a little bit tricky because when you increase the Manning's N values on your 2D grid, it slows flow down. So what ends up happening is from a hydrology standpoint, you start to attenuate your flows a little bit across your 2D grid. So you get lower peak flows throughout your grid, but you've got higher energy losses. So adjusting the Manning's N values has some interesting effects that are not always predictable across your model area. But what we did see in general was that an increase in the N values did result in a slight increase to the stages. So we did play around with the N values, and we ended up increasing the N values uniformly across the grid by about 15%. And then as far as model resolution, we started off with the 500 by 500 foot model cell sizes. I tested some smaller resolutions. In the area that we're interested in mapping, which is primarily that flat valley, the Cache Valley, there's not a lot of hydraulic relief in terms of the water surface elevation gradient. So we don't get a lot of differences even when you make the cell sizes smaller because there's just not a lot of relief in the water surface elevation grid in that area. Certainly if you're in a steeper area, you're going to want to have a finer resolution, but for the overall flow that's coming into that valley area, the area that we're interested in mapping, I think the 500-foot cell size it's adequate to give you good definition on your water surface elevation grid.
Okay, good. One other question, or several questions came in, but one that's raised to the top here is, what methods did you use to determine rainfall losses and excess precipitation in your model? How were the roughness values set in the model, and how did you adjust them for calibration to increase everywhere or only in specific locations?
Yeah. So I talked a little bit about the Mannings already. The other calibration parameter that we used was the runoff curve number. And I should mention that we did this model in HEC-RAS 5.07. So the spatial precipitation, the spatial runoff losses wasn't yet built into RAS 507. So we had to spatially average our curve number for the areas that we were looking at for the calibration, and then spatially average across the whole area for the design runs, and apply that in outside of HEC-RAS, I'm sorry, and apply just the precipitation excess to the HEC-RAS 2D simulations. I think we're still in the preliminary modeling phase, so we're probably going to move this model into HEC-RAS 6.0 so we can integrate the spatial curve number and rainfall losses directly in HEC-RAS.
Okay. One other question here. What was the calibration effort dedicated in capturing the timing of the peak flow at the Cache River? There seems to be a shift when the peak occurs at the model and then when it actually occurs.
Yeah, there's a little bit of a shift still in when the peak is occurring. Part of that may be due to the fact that with HEC-RAS 5.0, we have to apply uniform precipitation against a pretty large area. So it's one of the things that we'll be interested to see as we move the model into HEC-RAS 6, where we can apply spatial precipitation, that when we run those calibration event, what will that do to the timing of that flood wave in comparison? But we didn't put too much effort into correcting the timing, since we knew that with the limitations in RAS 507 that we couldn't fully account for that. So that's something to look at as we move forward with this.
Okay, one more question, I guess. How did you finalize, or are you finalizing the regulated floodplain given the 48 total scenarios with and without levee and sunny day?
That's going to be, an ongoing consideration and conversation with FEMA and the state as well. There's the potential that Reedsville levee will pursue accreditation. That we're still working that out with FEMA and the Corps of Engineers and the drainage districts to see what they want to do there. It's unlikely that the Karnak levee system is going to be able to pursue accreditation. So we're looking at the worst case scenario when it comes to the Karnak levee on both the lower cache and then the main ditch side. So the with and without extremes. And then for Reedsville, it's just going to depend on whether or not they're able to achieve accreditation for that. So there's still work to be done on finalizing which scenarios are ultimately going to go on the map for this project.
Okay, I think that's all the time we have for questions right now. I think we can move on to our next presentation. Thank you very much, Chris. That was very interesting. Our next presentation is Understanding the Importance of Hydraulic Controls and Mesh Resolution in 2D Hydraulic Modeling. And the speaker for this is Scott Hogan. Mr. Hogan has spent more than 30 years working in the field of river engineering hydraulics. For the past 15 years, he has worked with the U.S. Federal Highway Administration and was a consulting engineer prior to that. He graduated from Colorado State University and lives in Fort Collins right now. He has a BS and MS degree in civil engineering from Colorado State University. So take it away, Scott.
Sit in on this session and specifically my presentation, which today is focused on the importance of understanding hydraulic controls and mesh resolution in 2D hydraulic modeling. In my position at the Federal Highway Administration's Resource Center, I've had the opportunity to work closely with state departments of transportation and their consultants, providing technical support and assistance with hydraulic model review. Over the past several years, I've reviewed numerous models, and I've seen a wide range of mesh configurations, many that are pretty good and many that could use some attention. Bottom line is that we know that 2D hydraulic modeling is a great tool, but we continue to learn best practices that improve accuracy as well as efficiency. And the main purpose of my presentation today is to share with you some of the things that we've learned. When developing a mesh for a 2D model, our main goal should be accurately representing the terrain such that the accuracy of the results is consistent with our application. If we were only interested in accuracy, we could use very small elements to represent the entire model domain, but that results in long simulation times. So we're also interested in efficiency, as well as learning how to use this model most effectively. So based on the models that I reviewed to date, I tend to see folks that do SRH2D modeling to select element sizes that are much smaller than needed, resulting in very large mesh sizes and long run times. And those using HEC-RAS2D tend to use too large of elements, mainly because of the detailed representation of the terrain along each element face. But they often miss hydraulic controls, and they do not consider that there's only one water surface elevation computed for each element. And this is an important consideration in areas where hydraulic conditions are changing rapidly. Now, when most talk about performing sensitivity analyses, when calibration data is not available, they typically are referring to changing Manning's roughness values or downstream water surface elevations to see how sensitive the model results are to those changes. But few actually look at the sensitivity to mesh element size, and specifically how well hydraulic controls are represented in the mesh. So to emphasize the importance of representing hydraulic controls and selecting an appropriate mesh size, I've prepared a case study on a project located on the Eel River in Indiana. Project is located where State Route 46 crosses the Eel River, with a bridge on the main channel and a relief structure in the right overbank. And the flow here is from top to bottom. Here's a close-up image of this crossing and a close-up view of each bridge, main bridge, and the relief structure. And if you're not familiar with SRH2D and the SMS user interface, these bridges here are shown and they're generated by the 3D bridge tool in the SMS interface. And these 3D bridges can be used to evaluate two-dimensional pressure flow, as well as the geometries are used in computing bridge scour. But for the case study I'll be presenting, since there's not pressure flow, in this case they're only used for graphical purposes. The relief bridge here shown on the left, it actually has some history. It's failed and been replaced in the past, and yet the state of Indiana is still having issues with the scour, actual scour being greater than what's computed. In other words, so they've computed scour with a HEC-RAS 1D model, and the scour is exceeding that. So it's raised many questions. And so to further investigate the issue, the state added a flow gauge at this relief structure to complement the flow gauge that's already at the main bridge, was put in by the USGS. And so we're pretty fortunate to have measured flow splits for this case study over a range of flows for the past several years. And for that, I would like to thank and acknowledge Mark Bailey, the Chief Hydraulic Engineer of the Indiana Department of Transportation. And while I have this image displayed, I want to highlight what I'll be referring to later on as primary hydraulic controls, which include the roadway embankment, a berm upstream in the left overbank, and another noticeable berm in the right overbank. And now these each serve as hydraulic controls, meaning that they essentially control the water surface elevation upstream of these structures as well as the flow direction. With all 2D models that I'm familiar with, it's important to align element edges with these hydraulic features. Because if the tops or crests of these features don't align with element faces, then these features are not going to be represented correctly. And so basically, if the features are located inside or through the middle of the element, it won't see the flow across that element or compute the flow correctly. So arcs, such as these shown in this image, are used as break lines in the mesh generator or just in the process of generating the mesh. And what these break lines do is that they force elements to be formed along those features to ensure that the edges are aligned. Now, in many cases, the channel break lines also act as hydraulic controls, but mainly because the channel banks can control how much flow splits into the overbank and just basically influences flow distribution. But it's not always readily apparent whether or not this is the case. So I consider just generally a best practice to include break lines along channel banks where they're pretty noticeable features, or especially when you're trying to evaluate how much flow spills into an overbank area. And in addition to primary controls, another thing we look at is basically greater detail or representing secondary hydraulic controls. So we've already identified those main features, but there's also additional valleys and ridges that, if represented better in the mesh, we find, especially in SRH2D and somewhat in HEC-RAS2D, that they provide better results. So when I refer to secondary break lines or hydraulic controls, you'll see all these additional detail break lines added. And in fact, this mesh is one I'll refer to later on. This mesh size ranges from about 30 feet to 200 feet. All right, so it's focusing the detail in areas where there are either valleys or ridges. So for this case study, we're fortunate to have measured flow split data for 3 high flows. The first one shown in this image is about 6,500 CFS in the Eel River, and you can see, according to this table, about 240 CFS splits off to the relief structure. And for each of these cases, the flow split is significantly controlled by what's going on around in this bend, both the geometry and all the contraction of flow. So it's important to represent that. And that's pretty challenging to do in a 1D model. And later on, I'll show you the results from Indiana from their 1D model. But the 2 high flows here span the full width of the floodplain with about 18,000 CFS at one flow and 36,000 at the other. And I might note that for all of these flows, none of them overtop this roadway embankment. Okay, so that's important to note for this analysis. So all of the flow is going through either the main structure or the relief structure. And relative to the 100-year event, which is 48,500 CFS, this high event 36 is roughly 70% of that 100-year flow. Now, once Indiana DOT had measured or gauged this flow over a period of years, they ran a HEC-RAS 1D analysis to see what it predicted compared to the measure flows. And as you can see from these plots, it didn't do too well. In fact, at the high flow condition, you can see that the HEC-RAS 1D model underestimated the flow through the relief structure by about 2,000 CFS. Right? And that equates to about 2 feet in water surface elevation. And there was also pretty significant differences at the 2 lower flows. So with this, Mark Bailey and his staff were getting more curious about the benefits of 2D modeling. So they decided to do a blind modeling test, meaning that they requested SRH2D models and HEC-RAS 2D models to be completed for these flow conditions without knowledge of the measured data. So Mark reached out to me to do the SRH2D analysis, and he reached out to his consultants to do the HEC-RAS 2D analysis. And here are the results. Right, as you can see, they're not spot on, but considerably better than the 1D analysis. So you can see at the higher flows, there's a little difference, but still not too bad. And similarly for the middle flows and the lower flows, it just provided a much better representation. So I basically took this data and took it to another level. And I ran a whole series of tests using both HEC-RAS 2D and SRH 2D, the current versions of each. Except HEC-RAS 2D, there was a beta 3 version that came out in the midst of my analysis. So most of these results, or all of these results, reflect beta 2, but I did some spot checks and with beta 3, I didn't see any significant changes. What's listed here is a partial list of some of the key features in each package. They're actually quite similar, but there's a couple key differences worth noting. The one thing I really want to note is that the diffusive wave option, which is the default computational method used in HEC-RAS 2D, should not be used for detailed bridge hydraulic analyses. So it's best to change to the 2D full momentum equations or shallow water equations, and that's something I see missed quite often. Another thing to note, actually doesn't apply to these case studies, but as of late, version 6 came out with 1D bridge structures that can be inserted into a 2D domain to compute pressure flow. And SRH 2D also has true 2D pressure flow capabilities. So that's a significant improvement. Also, as I noted earlier, SRH 2D has a capability of building 3D bridges that can be used for those 2D pressure flow calculations, as well as supporting the scour calculations. HEC-RAS 2D has multi-core processing capability, which really does have benefits for many cases. But for these cases, actually, SRH 2D has a kind of a simplified steady state computation method that focuses on providing accuracy at that end result and sacrificing accuracy on those interim outputs, since we don't need them for steady flow. And so even though it's single core, it still runs pretty efficiently. And so I'll show that here shortly in some of the summaries. Another thing I want to highlight, and one more thing is that SRH 2D can also run multiple simulations at once on different cores. So that's not multi-core processing, but it can run multiple simultaneous simulations. Another thing, as I mentioned earlier, SMS with SRH 2D does have a tool that automatically delineates features, so basically valleys and ridges that can be used as break lines in generating meshes within SMS. And also it has tools for computing bridge scour and exporting those values to the hydraulic toolbox. FHWA clearly does have a preference for SRH 2D. Since we've been partnering with Bureau of Reclamation, who developed SRH 2D since 2013, and we've been working with them to specifically develop modeling and tools applied to transportation hydraulics. Now, many of the new features in HEC-RAS are impressive, and we'll continue to test them. But we will continue to have additional training for using those features for transportation hydraulics, as well as resources for how to review those. So stay tuned for that. I think we're going to continue to see a lot of changes for that in HEC-RAS 2D. But okay, enough said on that. Let's move on to this case study. So real quickly, first of all, this case study involves a reach that's about 5 miles long in the Eel River and about 1 mile wide. I did use the same information for both the SRH 2D and HEC-RAS 2D models, so the same limits, same terrain data, same Manning-Zand value, boundary conditions, same simulation time. The only things that were different were the time steps. In HEC-RAS 2D, I used the automated time step routine that basically sets the time step to meet a courant condition of approximately 1.0 or a little higher than that. And in doing that, I noted the time steps were generally in the 5 to 10 second range. In SRH 2D, it doesn't have that courant constraint, but you set the time step to make sure that mass is preserved, continuity is preserved, and that the solution is stable. And also, as I mentioned earlier, SRH 2D has a steady flow mode for the full momentum equation, so it does run pretty efficiently. Before I go on, I do want to express my appreciation and thanks to Mike Brown of Tetra Tech. He made himself available to review my HEC-RAS models. I have quite a bit of experience in SRH2D, but not as much in HEC-RAS. So it was helpful to have somebody who's much more experienced with HEC-RAS 2D to review them and confirm that what I was doing was correct. So thanks to Mike. For this case study, which was somewhat of a research project, I ran a whole suite of tests, if you will, or suite of simulations, varying the mesh size from 200 feet in nominal size down to about 20 without break lines, and similarly from about 200 feet down to 50 with break lines. And then I did run this last case with both primary and secondary break lines, as I showed earlier, with element sizes ranging from about 300 to 200 feet, okay, for all three of these flow conditions. Okay. So in the following slides, I'm going to show you an example of what each mesh looked like, and then a quick overview of what the results were. But not to worry if I go too quick for you. At the end, I'll show you a summary of all of the conditions and the results for the low flow simulations. So to start with, here's just a quick look at the 2D or the 200-foot mesh elements for both 2D models. See SRH2D on the left, HEC-RAS on the right. I do want to note that I did add a break line and added detail for both models along the roadway embankment and within the bridge opening, just to make sure that that was held constant and represented correctly. And so then I varied the element size and break lines upstream and downstream of that crossing through all these scenarios. Okay, so for this first one, here were the results with the 200-foot elements. Really not that good. Really both missed the mark. You can see SRH2D is far off, overestimating the flow through the relief structure by 3,000 CFS, and HEC-RAS overestimating by nearly 2,000. So really not acceptable. If we drop that down to 100-foot spacing or 100-foot element size, right, results improve quite a bit for HEC-RAS 2D, not as much for SRH2D. And then we can drop that further to 50-foot. Right, you can see this is getting pretty dense. And then again, marginal improvement on HEC-RAS, but not so much in SRH2D. As we'll see here shortly, SRH2D really does best with the break lines. Okay, and so we're going to jump back to the 200-foot element size, including break lines. Okay, one thing I want to note, let me jump back here. If you look at the time for this 50-foot mesh was about 40 minutes. Now, and I didn't show the 20-foot mesh because basically the screen turns black. They're so small. The results were improved, but the time to run each of these models was roughly 5 to 6 hours. Right, so I didn't even consider that practical anymore, and moved on to these other scenarios. And so you'll see that we drop from that 40-minute range quickly back to this 3 to 6 minutes, and you'll notice that the accuracy is much better. Okay, still not the best, but we continue to see improvements in both models, and quite a bit more in SRH2D when we start adding those break lines. And we continue with the 100-foot mesh. You'll see a lot of improvement in SRH2D. Surprisingly, the HEC-RAS 2D solution for the high flow did not continue to improve. I'm not exactly sure why. I looked at several other scenarios, looking at depth varied roughness, looking at changing the mesh resolution through the bridge openings. And there were some minor improvements, but not what I was looking for. So this is something I'll continue to have to look into further. But I do want to show you that last scenario with the mesh that it represents both primary and secondary break lines with elements that generally range from 30 to 200 feet. Really efficient run times and really good results across the board. Still some exception for that HEC-RAS 2D at that high flow, but I just need to look into that a little more. But you'll see that this is kind of really a sweet spot for SRH2D. It dialed right into all the three flow conditions. Now this is a summary for all of those scenarios at just the low flow. It's really the low flow really was the best at clearly highlighting these trends. So you can see the plot on the left for SRH2D. You can see really poor performance at the 200-foot mesh size. As you drop down to 220, it's good. And then there's a similar trend for HEC-RAS, but not nearly as bad as SRH for the large elements. Again, both were pretty good at 20, not right on the money, but pretty good. But then as soon as you add brake lines, look at this, HECRAS just dials right in. Even with 200-foot elements, it does really well. For SRH2D, there is improvement, but you'll even see like a 200-foot element size with brake lines, it didn't show any flow reaching that relief structure. Some improvement with the others, but again, its sweet spot is this, I think, using both primary and secondary brake lines with that variable element size. I did see some improvement there with the HECRAS models, not at this flow, but the other flows did show some improvement. So I still think it's worth looking at, but the HECRAS models, this demonstrates the importance of at least primary brake lines in any of your models. Right? So a lot of information, and I know I'm running short on time. So I want to close out with some best practices for detailed hydraulic modeling analyses. I rarely recommend using brake lines to represent the primary hydraulic controls, such as roadway embankments and berms. Channel brake lines were appropriate, I'd say probably in most cases, not always, but then also guide banks, dikes, and other linear features. Using those brake lines helps to ensure that the element edges align continuously along that feature, but also check model sensitivity. I wish from this case study I could give you a magic number, but I think it's going to be fairly project specific. However, I do believe that 200-foot element size is probably at the upper end of the reasonable range for detailed hydraulic analyses. And I would dare say that at least probably closer to the 100-foot element size. And honestly, that applies to both SRH2D and HECRAS. I think SRH2D benefits a lot more from the secondary brake lines to represent the details, whereas HECRAS does that with its detailed terrain representation of each element face. But there's still benefits there. So that's my last point. And so with that, if you have any further interest in this topic, please consider joining our 2D modeling users forum simply by sending me an email. And you may be interested in some of these other resources that I've got listed, 2D reference document, training, tutorials, and videos. Just go to our website listed there. And as always, feel free to contact me with any questions. Thanks for listening, and I wish you the best in your future modeling endeavors. Take care.
Well, very good presentation, Scott, and very interesting. Again, your graphics were lovely. We've got a number of questions, so I'll jump into them right away. The first question that popped in was, what's the significance of cell shape, structured versus unstructured in calibration?
All right, thanks, Alan. Good question. Really, regarding cell shape, there's no significance regarding calibration per se. It's more sensitive to cell or element size, but the shape itself doesn't matter in calibration. The shape does matter in computational time. Typically, the simpler the shape, more rectangular the shape, the faster the computations. But the shape itself does not have any impact on calibration.
Got another question here. Did you use the infiltration option in RAS, and how does SRH compute the rainfall losses?
I didn't use any kind of precip analysis. This was purely a peak flow analysis. SRH does have rainfall capabilities and infiltration and losses, but that's not something that's pertains to our transportation hydraulics and peak flow analyses.
Okay, we have a question here also from Brooke Seymour. Have you had an opportunity to compare pressurized versus overtopping bridge results between HECRAS 2D and SRH 2D?
It's a great question, Brooke. That would have been a great addition to this case study, and I'll have to look at that more in the future, but it really gets a lot more in depth. To answer your question, though, I've done a few limited comparisons, and they are quite different. It definitely warrants more investigation. One of the big differences, I'll try to keep this short, in RAS 2D, the new bridge analysis approach, it's still a 1D bridge analysis, and it's based on sluice gate and orifice flow. And key in that is the assessment of a coefficient of discharge. And so it's very much simplifying the flow through that bridge. And so far, and in contrast, SRH2D is actually modeling the two-dimensional flow through that bridge and represents the pressure surface of the low chord of the deck and is evaluating pressure flow at each element. But it also has its limitations in that you have to assess a roughness or a Manning's N roughness and assign it to the ceiling or the low chord of that bridge to assess the shear stress, the loss. Both approaches really do need calibration. I've looked at, or I should say, I've been helping folks that have been comparing the two. They are quite different. So it really raises the importance of being able to calibrate a model. So it's something that we're going to have to look into more, but definitely be aware. From what I've seen so far, the HEC-RAS results are quite a bit higher, meaning the water surfaces are higher. So we'll have to look into the comparison of that drag coefficient approach versus the Manning's N and the shear stress computation. So thanks for that question, Brooke.
Another question is, are you able to manually adjust the automated brake lines if you have reasons to?
Great question. So the automated brake lines, so as I mentioned in SMS, it automatically delineates the valleys and the ridges, and it just adds them to a coverage. And from that point, you can delete the ones you don't want to use. You can certainly edit them. They just become arcs that you can manipulate as needed.
All right. Did you say the feature line should match the mesh lines?
Feature lines, if I understand the question, and let me clarify this, is that what I did say is that it's very important to make sure those brake lines, or maybe you're calling those feature lines, that they align consistently along hydraulic controls. So it's very important that element edges get placed along those controls. Otherwise, the controls will not be represented correctly.
Well, I think that's about all the time we have for questions. Thank you very much, Scott. That was great.
Thanks a lot.
We'll now move on to our next presentation, and that is machine learning insight for rapid inundation screening. And our speakers are Mark Bartlett and Jeff Albee. Mark is a senior engineer at Stantec and has delivered a variety of water and watershed and wastewater projects, ranging from strategic planning to detailed design. Mark's research agenda advances the study of climate variability, surface and subsurface hydrology, stochastic, that is random processes, and ecohydrology, the interdisciplinary analysis of interactions between water and ecosystems. Jeff is a principal at Stantec with a career spanning 20 years focused on understanding technology trends and their influences on developing future engineering successes. Jeff's passion is focusing on people when delivering new technology, from how we use it to enhance our ability to deliver on it. So with that, I'll fellows, take it away.
Hello, ASFPM 2021, and thank you for choosing our paper on Insight, Machine Learning for Rapid Inundation Screening. I'm Jeff Albee. I lead our digital solutions team here at Stantec, and with us today, I want to recognize Marisa Henry, data scientist for Stantec, who had made significant contributions to this.
And Mark Bartlett with Stantec. Right in the background here, we're looking at machine learning produced results provided by the platform that we'll be going over. And the question is, can previous model results inform future flood risk mapping and rapid risk warnings from forecasts, specifically for pluvial modeling? And can this be informed by the modeling that we're doing for HEC-RAS right now? And pluvial modeling or pluvial flood risk is an important component of flood risk assessment. And as was seen with Hurricane Harvey, most of the homes damaged by Harvey were outside the floodplain. And historically, FEMA hasn't mapped pluvial flood risk, only riverine flood risk. And just for a refresher, pluvial flooding is when it's rainfall-induced flooding. So there's riverine when the river overflows its banks and causes flooding. And then there's pluvial flooding, flash floods, where you have the rainfall intensity exceeding the infiltration capacity of the soil or the drainage capacity of the urban drainage system that causes flow to accumulate and then create flooding in streets, for example. And it's an important factor or component of flood risk to capture because 80 to 90% of annual flood deaths are caused by flash floods or pluvial flooding. And approximately, not surprisingly from what we just mentioned, 40% of these fatalities are associated with pedestrians and crossing streets or vehicles that get trapped in high water that accumulates in streets from these pluvial floods. And it's important that we capture this because it's only going to get worse in the future. Climate change is projected to increase heavy precipitation events in the future, and this map showing the heaviest 1% of precipitation. And so we would expect that our 10-year event or 100-year event and so on would increase in intensity in the future, leading to more pluvial flooding. So it's important that we're able to rapidly predict where this where the flood extents are, say given a rainfall forecast, so people can get out of the way of the floods and we can mitigate them as best as possible. So currently we have a status quo where past models often do not inform future models or rapid risk prediction. And in conjunction with that, we have hydrologic models that often have many parameters, so you can often have statistical overfitting. So for tracking, for example, soil moisture evolving in time, we might not necessarily be on the right trajectory of soil moisture, which could lead to an under overestimation of the runoff that is essential for driving the flood mapping. In addition, if we have the runoff, we can't just run HECRAS to get a result quite rapidly necessarily. We need that answer quite fast because oftentimes forecasts can happen quite rapidly. The forecast can change quite rapidly. And so if a heavy precipitation event is forecasted, then we need to be able to rapidly map that to its extent so we can warn people. A way forward is using existing model runs that form a data-driven approach that's fluid for rapidly predicting pluvial flood risk. And so we couple this to a simple approach that doesn't look at soil moisture, one trajectory of soil moisture, but looks and captures the statistics of soil moisture and runoff as functions of integrated weather in real time. So integrate frequency of rainfall and average rainfall per storm event. In turn, this provides for reasonable runoff estimates that are rapidly mapped to the watershed to determine pluvial flood extents via machine learning. And all of this is codified in a platform that we call Connect.
Thanks, Mark. So as he said, our way forward is the Connect platform. And it's a simplified technology platform that really does empower our digital science engineering, turning data into our most valuable asset for our projects. Connect contains 4 modules, all interact together to deliver results for our clients using data. And we've seen great results using the Connect platform, our simplified technology approach, digital approach. We're generating models over 7 times faster using Connect. And as Mark's about to show, we're delivering very high accuracy machine learning data insights. Those are typically over 80% accuracy and providing those insights very quickly, as well as taking a new DevSecOps approach. We're rapidly deploying these solutions for our clients and customers around the world.
Thanks, Jeff. So as Jeff mentioned, we're going to be discussing the flood component of Insight. So we'll first start with how we capture soil moisture and then turn that into a reasonable prediction of runoff. We'll look at how that compares to data, and then we'll look at how we turn the runoff into a flood extents mapping using machine learning. And then finally, we'll discuss the machine learning results and go over any questions. Soil moisture and tracking that in time is one of the most important hydrologic aspects for getting a reasonable estimation of runoff, because soil moisture is a master variable. It accounts for soil, it accounts for vegetation, and it accounts for climate factors. And when we're discussing climate, we're considering average storm depth per storm event and the frequency of storm events. And so if we look at a 30-day window, we can integrate this from weather data and then use that to get a reasonable estimate of soil moisture moving forward in time. And this is essential because if we look at soil moisture as shown with the data here, it decreases in time because of evapotranspiration, plants pumping water out of the land surface, and then it increases in time because of rainfall events. As we can see, the rainfall is quite sporadic, and so consequently so is the soil moisture. So if we do have a statistical overfitting, it's likely that we could find ourselves in the wrong trajectory. But if we capture the statistics, we're likely to capture an average as reasonable, as I will show, for predicting what that runoff amount is. So as I said, instead of just capturing one trajectory as shown with the black line over a season, where we, this could be representative of the Northeast, which is one of our study areas, where in the winter we have a wetter soil moisture because we have less energy coming in from solar radiation. The trees have lost their leaves. And then during the summer, we have a dry down soil moisture because of evapotranspiration and significant activity of plants pumping water from the soil to the atmosphere, which is associated with stronger solar radiation. Differently, as I mentioned, we're not just capturing one trajectory, but we're looking at any slice of time. What is that distribution of soil moisture? And we're looking at how that distribution evolves in time. And we have an analytical solution for this shown with the black line. And the equation for that is shown in the top right. So it's relatively simple. There's a bit of complexity involved here, but it compares quite well to the Monte Carlo approach, which is shown with the gray bars. But we get this much faster because we have to generate thousands and thousands of Monte Carlo samples and bin them and then create the distribution. And differently, we can go under the hood here more later during questions, but because we're looking at a distribution evolving in time, we're looking at the frequency at which soil moisture upcrosses a certain rate, upcrosses a certain level, and downcrosses a certain level. And if soil moisture is frequently upcrossing and downcrossing a certain level, that corresponds to a higher probability of soil moisture actually being in that state. From the soil moisture distribution, we can also get a distribution of runoff. The two are coupled together. And this has an explicit dependence on rainfall frequency and rainfall amount, which we can integrate over a moving window from weather data to get the average, to get this distribution of soil moisture from which we can calculate the average, and then in turn get the runoff from this distribution here. It depends on vegetation, so we can integrate that, so we can move to different areas of the country. And this is integrated through evapotranspiration, a function for that. It depends on the runoff model. So here we're using the curve number method, although we're not limited to that. We can use different models. And each model has a different assumption for the distribution of spatial heterogeneity or for spatial heterogeneity. So once we have this model, we have an average soil moisture, which we get from that distribution. We can look at this on a yearly basis, and we can calibrate some of the hydrologic unknowns, in particular the hydrologically active soil depth, so that we match relationships that are universal across a variety of environments. So one of those is the Boudico curve, which describes theoretical energy and water limits on a catchment water balance. So the x-axis describes potential evapotranspiration divided by precipitation. So it's like a dryness index. So for at 0.1, we're in a wet environment. Or for at 1, we're at a dividing line between an energy limited environment on the left. So we don't have enough energy to actually evapotranspire the water that's coming in. So we have more runoff, which is shown above the black line here. And then we transition to a water limited environment where we have plenty of energy. So we have lots of evapotranspiration and that corresponds to between the dashed line here and the solid line here having much less runoff. And as you get drier and drier, pretty much everything just gets exported to the atmosphere through evapotranspiration. So we can calibrate to this, and we get pretty reasonable results as I will show with this data comparison. So for example, here we're looking at the New York area. We can look at average precipitation for storm events over a year. We looked at the data for this area. We calculated what the average precipitation is for storm events for a year typically. Now, if we were to integrate this over a 30-day moving window, say for 2018, we can see how this compares. In 2018, in the summer months here, there was a marked increase in the average precipitation for storm events. And the same goes for the frequency of storm events. We have the typical year with the blue line. And then if we look at a 30-day moving window, we have the red dash line. And there's also a marked increase in the frequency of storm events. And this translates, so our model of soil moisture picks this up. And we can see the model here on the right. The blue line shows the typical year. And the dash line shows 2018. And 2018, associated with that integrated value of frequency of storms and average amount of precipitation per storm, there's a marked increase in soil moisture as shown with the yellow highlighted area. And this compares quite well to data. So in the fall, we see this marked increase in soil moisture. And here we're looking at data. In the fall, typically it wets up to the red line for each year. But in 2018, it's well above the red line. And this matches with our model. And as we can see, the soil moisture contains a memory of weather and climate that's happened in the past. So it's quite important to capture that. But not only soil moisture, we capture, of course, runoff quite well too. So the model, the average runoff from the model is shown with the gray line, and the data is shown with the black X's. And so we have a reasonable match between the model and the data. But we also have a reasonable match for the variability around the average values for the winter wet season, where the model is shown with the black line, the distribution of runoff, and the data shown with the gray bars. For the spring dry down, there's a reasonable match for the summer dry season, as well as for the fall wet up. So we have the ability to integrate weather data and get a reasonable measure of the average soil moisture and get a reasonable estimate of runoff given a precipitation input from a forecast. And we can now take this and we can map it to flood extents using machine learning. And we do this by incorporating runoff into factors that describe the potential for flooding for any point in a watershed. So here we're looking at runoff intensity, as I'm showing with the cursor here, and it's multiplied by the contributing area. And this gives us the flow, the approximate flow, very rough, for any point in the watershed. So by a point, we're looking at the green point here. We map that to its nearest flow path. And from the nearest flow path, we can get this contributing area. So we have the contributing area coming into this cross section, or the rough flow coming into this cross section here, and that is normalized by the capacity of this cross section to transport flow. And this is based off of velocity given by Manning's equation, multiplied by a rough representation of the cross sectional area, which is given by the height above drainage multiplied by the distance from drainage. And now this cross-sectional area isn't exactly correct. It's roughly correct, and it scales as we look at different points across the watershed. But the machine learning, since all these factors are multiplied by a weight to predict flooding, machine learning will correct for this for these differences. But the important thing is that we're roughly capturing the physics of what is occurring, and so we feed in these scientific and engineering informed factors to improve the prediction of our machine learning model. And all these factors can be derived or taken from a DEM using algorithms that are out there in GrassGIS and so on. And here we're showing how we calculate using GIS the contributing area. So we can see the light pink shows where the contributing area is quite high, which are the main river and the significant stream reaches. And the green shows where the contributing area is smaller. So these would be the local streets where flow is starting to accumulate before it's flowing into the more prominent flow pathways. And we can define this flood potential factor looking at what I'm calling the non-local flow paths, or the more prominent stream and river reaches. So we can look at a point in relation to this and then calculate that factor as I described previously. As well as calculating it in relation to the local flow paths, where we define these flow paths with a lower threshold for accumulation. So we get these two different factors that are both informed by the model, by the physics of the hydrology and the hydraulics. We take these various factors, so the non-local, what I call the non-local insight flood factor and the local insight flood factor. We take distance from drainage and height from drainage. These are the inputs to the machine learning model. Different weights are given or multiplied by these inputs to create a net value. And then this is used to create the logistic. So in this case, we're using a logistic regression, which provides us a distribution of probability of the likelihood of flooding for, say, 100-year events. We then say if the probability of flooding is greater than 50%, it's flooded. If not, it's not flooded. So so that thresholding of that 50% value is basically unit step function. And then the machine learning model iterates through the weights to find the correct weights to provide the best match between the machine learning model answer and the HEC-RAS model basis. But once we have that, we can supply different runoff values to get different levels of flood extents, as well as extending this to different areas where we haven't run a HEC-RAS model, supplying that runoff value and getting the flood extent. So it provides a way of using the HEC-RAS model to create a data-driven approach that has a life of its own for aiding in additional predictions to help save lives, to help inform risk, to help take mitigation measures, for example. And now I'm going to go into some of the machine learning model results that we observed for two different case study areas. So we looked at both around the Passaic River in New Jersey and around the Des Plaines River outside Chicago. We looked at a 10-year event. The accuracy is around 86%. And accuracy here is defined in the true positives plus the true negatives. So the true positives are where the machine learning predicted flooding, and the HEC-RAS model also predicted flooding. And the true negatives are where the machine learning model didn't predict flooding, and the HEC-RAS model didn't predict flooding. And so we have the true positives and true negatives up top, and these are normalized by the true positives and the true negatives, plus the false positives and the false negatives, so where the model mispredicted. And this can also be viewed as an area under curve. So we have our true positive rate versus our false positive rate. Ideally, we want a true positive rate that goes to 1 and the false positive rate to then cut over to 1 here. That would be a perfect model prediction. So we're around 0.91 for New Jersey and 0.87 for Chicago. Compared to values in literature, primarily for riverine, this is pretty good. Values on the high end range from say 0.85 to 0.95. And here we can see how the HEC-RAS model result compares to the machine learning results. It's not perfect, but it's not meant to be perfect. It's meant to provide a rapid, reasonable estimate of flood extents, and this can also be improved in the future by adjusting the features, incorporating new data. It can grow as the HEC-RAS modeling effort grows itself. It's not limited to what's being shown here. It's very dynamic. This is the initial 10-year event run, but this can be improved over time. And for a 100-year event, we have a 78% level of accuracy. The area under curve is still quite good, 0.89 for New Jersey, 0.86 for Chicago. And if we go to the map, we can see, of course, the flood extents are much larger now, as would be expected. Still, there's room for improvement, of course, but it does capture the areas where flooding is occurring. It does capture those flow paths. So, if we were to fine tune the features a bit more, say the threshold for how we're defining that local flow path, I would say we would improve the results here, as well as in this case, New Jersey and Chicago were considered as one model, but if we were to split them up into separate models and account for that variability or the difference in precipitation for a 100-year event in New Jersey versus Chicago, we can improve this, because a 100-year event precipitation in New Jersey isn't going to be the same as a 100-year event precipitation in Chicago. And for the 1,000-year event, we have a similar level of accuracy. Area under curve is still quite good. And again, that does compare quite favorably to what folks have observed in the literature. So it's up there in the higher end of accuracy and predictions. But it does provide that pluvial flooding, which is a missing component oftentimes in flood mapping efforts. And here again, we can compare the HEC-RAS model result and the machine learning model prediction. It's much greater, but we're observing similar patterns with the 10-year and the 100-year. So in summary, we can use the simple hydrology model to capture rainfall statistics. So the frequency of rainfall and the average amount per storm event. And we can use this to provide reasonable and real-time estimates of soil moisture and runoff statistics. We can in turn use the runoff values and map them rapidly based on a data-driven approach, machine learning in this case, that extends the life of historic modeling efforts. So your modeling efforts are living in a sense. They help you make decisions moving forward in time. And then model physics inform the machine learning model feature. So provide for a reasonable measure of flooding potential. So it's not just about throwing data at the machine learning models. How do we transform this data into measures or features that align with the physics that's going on to aid the machine learning model in providing reasonable results? And when following this approach, machine learning may provide for rapid estimates of flooding at a level of accuracy that's suitable for warnings and initial assessments. So if we have a rainfall forecast coming in, we can turn that into runoff and then rapidly map where the flood extent is expected to occur, and then send out warnings on someone's phone or through a website or through an alert to make sure people stay off streets that are likely to wash their car away. And we're happy to take any questions.
Thanks, Mark. Good job.
Thanks, Jeff.
Wow, that was a great presentation, Mark and Jeffrey. I've got a number of questions that have come in here, and thank you for submitting questions. I'm going to ask one question first. It's a little lower, actually, but did you use the National Hydrography Dataset to develop your local flow paths?
We used it for the main reaches. We burned them into the DEM for what you saw. But for the ones that were defined on a finer basis with a lower threshold for flow accumulation, that was based off of the DEM itself, so 3 meters in this case. Using GrassGIS to calculate the drainage directions. Yeah.
Okay, another question from, and how long, oops, I just lost that question. How long does the soil take the moisture memory in your analysis, and to what depth of soil moisture content was measured?
Well, in our case, we're considering the curve number method, so it would be the model itself would conceptually capture the entire watershed moisture content. But the SMAP satellite just captures the first 1 meter. So we're using that to gauge the overall behavior, what's happening. But in terms of the memory that the soil moisture has, I would have to get back to you on that. There are works out there that have looked at how long the memory persists, and that's going to vary depending on the frequency of rainfall and the climate regime that one is in. But I don't know that offhand. But if you email me, I'm happy to send you something on it.
Question here also is, did you do a sensitivity analysis to see the influence of the various inputs to your machine learning algorithm results?
Yeah, we did. We found that height above drainage, distance from drainage, runoff, of course, and then that dimensionless factor that we had described is very sensitive to those. We looked at some other factors too, like land use, soil type, but the factors that captured the model physics were the ones that had the greatest impact in influencing the results.
All right, another question. It's a comment, very cool applications, Mark. And then it says a couple of questions. What sort of documentation is required with submittals? Some view ML, machine learning, as a black box, but this seems like kgml, and more defensible? And then 2, how scalable is this to national results?
Let me take some of that to start, Mark. Jeff, we're working through what actual submittals are, so I'll let Mark describe some of the documentation that we've got. But you're right. Your second point does feed the first one, that it's not really a black box, and that's why we're showing off what we have here. It is a bit more defensible, and it does come with accuracy results against what Mark described as true positives and false positives. So there is some comparison there of those two things, and we think it does scale to a national analysis and more of a regional analysis, and that's what we're trying to compile in the Connect platform. And with that insight piece is to build up regional capability to apply these ML processes to a regional scale and regional conditions, and deliver those results very quickly and with this process. Mark, do you want to over answer some of those things as well, in each of those points? Help me to clarify from the science perspective.
Yeah, in terms of being defensible, we're taking the approach of defining the features based on the model physics. So we showed one, for example, there. Another one would be the geomorphic unit hydrograph, which we're incorporating in. So when you do that, you basically developed a kinematic wave model for the entire watershed. Of course, with any model, there's some uncertainty around the parameters. And in this case, they're the parameters of the logistic regression. But we're doing the fit to find those parameters based off of the HEC-RAS. So it's similar in that sense to a traditional modeling approach, where we have unknown parameters and we're fitting them. But in this case, every time we, for example, for logistic regression, we add a parameter, there's another set of data that comes with it. So we always, when we're adding parameters, we're adding data to support it. So that helps to make the results applicable to additional areas.
Yeah, so we think that the speed in which you get these results, often seconds, is worth the sort of the accuracy results, which Mark described at 80 to 90% accuracy. So there's some value there in uncertainty based on the rapid results that you're getting from this process.
Another comment came in, or question came in. Have you considered integrating with local stream gauges? And they comment is a good presentation.
Yeah, I'll answer that one as well, and Mark maybe can describe how that would increase our accuracy. That is part of this. I know I keep doing commercials for the Connect platform and what we're doing. I'm not trying to over commercialize it, but that is the next part to what we're trying to do is be able to safely and securely interface with sensors in the field and bring that data back into the model to enhance our accuracy. So that is a later phase, and that is what we're planning to do. And I think you can see with all the cybersecurity issues in recent weeks and months that we're taking a very secure and pragmatic approach to how we do that. Mark, maybe you could illustrate how that would improve our accuracy. Should we be able to do that?
Improve the accuracy. Sorry, I was reading some of the questions.
Connecting to, yeah, that's okay. Connecting to stream gauges.
Oh, the stream gauges, yeah. Yeah, we could connect to stream gauges. So in this case, we're doing the pluvial flooding, but I would say we tackled that first. So the riverine would be the other aspect of flooding that we could tackle. And in that case, we could link it to stream gauges, or say, for example, the National Water Model.
All right, we're running short. I'm going to ask one quick question. How was the structural hydraulic limitations accommodated?
Yes, so it's accommodated implicitly through the original HEC-RAS model that we're training off of. So very much the quality of the machine learning results are dependent on the quality of the HEC-RAS models that are provided to it for training. So the higher quality of the HEC-RAS model result, the higher quality of the machine learning model results.
Well, very good answer there. That helped me a lot. I really appreciate all the speakers today. Chris, Scott, and Jeff, and Mark, really appreciate those. All very, very good presentations. I learned a lot today. So please go on now to the exhibit hall, and then the plenary, I think, will start at 11 o'clock. So thank you all for attending today. And again, thank the speakers. You did a great job. Thank you.